Imagine a boundless, stretchable fabric. This fabric is not just a metaphor, it represents the very structure of our universe. This fabric is space-time, the very essence of our universe. It weaves together the dimensions of space and time into a single, interconnected continuum. It's not an empty stage, it's an active player in the cosmic drama. Space-time interacts with everything within it, influencing the motion of planets, stars, and galaxies. Space-time is the backdrop on which galaxies and stars dance, and it's not static. It bends and warps in response to the presence of mass and energy, creating the gravitational fields that govern the motion of celestial bodies. Space-time expands, pushing galaxies apart like dots on an inflating balloon. This expansion is driven by a mysterious force known as dark energy which permeates all of space. This expansion is a fundamental property of our universe. It began with the Big Bang and has been continuing ever since, causing the universe to grow larger and larger. As space-time stretches, the distances between galaxies increase. This means that the universe is not only expanding, but also accelerating in its expansion. The farther away a galaxy, the faster it seems to recede from us. This observation, first made by Edwin Hubble, provided the first evidence for the expanding universe. This expansion is not the galaxies moving through space, but rather the fabric of space itself stretching. It's as if the very stage on which the cosmic drama unfolds is growing larger. It's a concept that revolutionized our understanding of the cosmos. The realization that space-time itself is dynamic and ever-changing has profound implications for our understanding of the universe and our place within it. When we observe distant galaxies, their light appears redder than expected. This shift towards the red end of the spectrum is not just a random occurrence, but a significant clue about the nature of our universe. This phenomenon, known as redshift, is a crucial piece of evidence for an expanding universe. It was first observed by Edwin Hubble in the 1920s, who noticed that galaxies are moving away from us in all directions. Light waves from these galaxies get stretched as they travel through expanding space-time. This stretching of light waves is akin to the stretching of a rubber band, where the more it stretches, the more tension it holds. Think of a siren moving away from you. The sound waves stretch, resulting in a lower pitch. This is known as the Doppler effect, and it applies to light waves as well. Similarly, stretched light waves appear redder. This redshift is a direct indicator of the velocity at which a galaxy is receding from us. Redshift tells us how much the universe has expanded since the light left those distant galaxies. By measuring the redshift, astronomers can determine the rate of expansion of the universe. The greater the redshift, the farther away the galaxy and the longer the light has traveled. This means we are looking back in time, observing the universe as it was billions of years ago. This relationship between distance and redshift is a cornerstone of modern cosmology. It helps us map the structure of the universe and understand its history and evolution. By studying redshift, we gain insights into the Big Bang, the initial explosion that created the universe, and the subsequent expansion that continues to this day. A common misconception is that the expansion of spacetime affects the speed of time. This is not accurate. Spacetime expansion influences the distances between galaxies, but it doesn't directly control the flow of time for observers within those galaxies. Time is relative, meaning it can flow differently depending on factors like gravity and motion. However, this relativity is distinct from the expansion of spacetime. To understand this distinction, we need to delve into Einstein's groundbreaking theories of relativity. Einstein's theories of special and general relativity revolutionized our understanding of gravity and time. They revealed that time is not absolute but is intertwined with space and is affected by gravity and motion. One of the most mind-bending predictions of relativity is time dilation. Time dilation means that time can pass at different rates for observers in different gravitational fields or moving at different speeds relative to one another. This concept is crucial for understanding why the expansion of space-time doesn't directly govern the speed of time. Section 5. Gravity's grip and time's dance: examples of time dilation. Let's consider some examples to illustrate time dilation. Imagine a clock placed near a massive object like a black hole. Gravity warps space-time in the vicinity of the black hole. Time slows down in stronger gravitational fields, so the clock near the black hole would tick slower than a clock farther away. Another example is a spaceship traveling at a significant fraction of the speed of light. Time would pass slower for the astronauts on the spaceship compared to observers on Earth. These examples demonstrate how gravity and motion can influence the passage of time. Section 6. Local clocks, cosmic time scales, differentiating temporal scales. While space-time expands on cosmic scales, it has no measurable effect on local time. Your wristwatch will not tick slower because of the universe's expansion. This is because the expansion of space-time is most noticeable over vast distances. On Earth, the effects of gravity dominate our experience of time. The gravitational influence of Earth determines the rate at which our clocks tick. We experience time locally, within the confines of Earth's gravitational field. However, when we look at the universe as a whole, we need to consider cosmic time, which is vastly different from our local experience. Section 7. Cosmic time versus proper time, two sides of the same coin. In this section, we delve into the fascinating concepts of cosmic time and proper time, exploring how they are intertwined yet distinct. Cosmic time refers to the timescale of the universe as a whole. It is a universal clock that ticks away the moments since the birth of the universe. It's the time elapsed since the Big Bang, roughly 13.8 billion years. This grand timeline encompasses the formation of galaxies, stars, and planets, marking the evolution of the cosmos. Proper time, on the other hand, is the time measured by an observer's own clock, within their specific reference frame. It is the personal experience of time, unique to each observer. Imagine you're an observer looking back at the early universe. Through your telescope, you witness the birth of stars and galaxies, events that occurred billions of years ago. You're seeing events that happened billions of years ago in cosmic time. The light from these ancient events has traveled across the vast expanse of space to reach your eyes. However, the light from those events traveled through expanding space-time to reach your eyes. This journey of light is a testament to the vastness and dynamic nature of the universe. Therefore, the time it took for that light to reach you is different from the time that has passed for you, the observer, in your own reference frame. This difference highlights the relativity of time, showing how cosmic time and proper time are two sides of the same coin, each offering a unique perspective on the universe's grand narrative. Section 8. The subjectivity of time, a biological perspective. Our perception of time is also influenced by our biology. Different creatures experience time differently based on their metabolic rates and lifespans. Consider a housefly. A fly's perception of time is much faster than ours. They perceive events in slow motion compared to our experience. A fly might see a swat coming in slow motion, while we see it as a quick movement. Conversely, a giant tortoise with a long lifespan might perceive time as passing much more slowly than we do. Section 9. Time in isolation, a thought experiment. Imagine floating in empty space, far from any stars or planets. With no external references, your perception of time would become distorted. Without the familiar cycles of day and night, your internal clock would drift. This isolation could lead to sensory deprivation and psychological effects that further alter your experience of time. Time might seem to slow down, speed up, or even lose all meaning. This thought experiment highlights the subjective nature of time and how our perception is shaped by external cues. Section 10. Conclusion. The intricate relationship between space-time and time. The expansion of space-time is a fundamental aspect of our universe, but it doesn't directly control the speed of time for observers within galaxies. Time is relative, influenced by gravity and motion, as explained by Einstein's theories of relativity. While space-time expansion affects cosmic timescales, our local experience of time is governed by Earth's gravity. Time is a complex and multifaceted concept, shaped by physics, biology, and even our perception. What are your thoughts on the nature of time and its relationship with the cosmos?